from these three problems and 7.2, the second half of 7.2. In this part of the homework, we are using the Laplace transform to solve differential equations. In number 35, you can see why Laplace transform will be useful when you work these as well for initial value problems. So when I apply the Laplace transform to the left, remember that the Laplace transform is a linear operator, so really you're taking the Laplace transform of each of those terms, and you can pull out the constants and deal with those later. So for y double prime, this is what I worked in my first video about Laplace transform, and this is a formula, so this is what we found, what we derived for the second derivative of a function. And so go back if this isn't familiar, this is in your textbook to help you remember that. So the Laplace transform of the second derivative will be this expression, s squared, the Laplace transform of the function minus s times y of 0, so that's y to the first degree, and then you'll subtract y prime of 0. So the powers of s go down there as the order of the derivative increases. Because that's only to the second derivative, you'll have these three terms. For the first derivative, I have these two terms. For the Laplace transform of y, I simply write that as capital Y of s to express that. Once you evaluate that and substitute your initial values, then you'll want to complete the algebra to simplify and solve for y of s. So once I get here, you'll notice I had three terms with y of s. I factored out y of s, combined those like terms. Anything that didn't have y of s, I threw on the other side, so that makes a positive s plus 5. I solved for y of s by dividing by that quadratic. That quadratic actually factors, so I'm left with a rational expression that looks like this. Because that quadratic factors into two linear prime factors, then I used partial fraction decomposition using the cover-up method that I described in the previous video and in class to unravel this. So I decomposed the fraction into these two terms, and then because I had it in a form where I could apply inverse Laplace transform, then I did as such. So 4/3 will be my constant. Here you have minus a, so I'll have an e to the negative 4t, negative 1/3, and then e to the negative t, because my a here is negative 1. So this was number 35, and yes, you will have to use partial fraction decomposition. It may slow you down a little bit, but for lack of, and I don't want to sound like I'm not understanding here, I only assigned these three problems. These problems can get quite involved, and so this is one of your easier problems. If you do have quadratic factors, you will be spending a little longer on this. A linear factor, I highly suggest you consider the shortcuts I've taught you. If you are still using systems of equations, it will slow you down, and then when you get to the quadratic terms, then your homework will seem quite overwhelming. So please consider those shortcuts I've discussed, and try and talk to me if they don't make sense. So on number 37, here you have a second order differential equation, and I applied the Laplace transform. So on the left hand side, you'll see for y double prime I have these three terms. For y, because that's linear, no derivative, I just have a Laplace transform. On the right hand side, from 7.1 or the beginning of 7.2, we have this expression. I have used the Laplace transform, so the square root of 2 remains because this is sine of bt, so I wrote the Laplace transform up here. Then b or beta was the square root of 2, and I have that over s squared plus 2, the beta squared. Use your initial conditions and try to solve for y of s. So simplify, combine like terms, solve for y of s. On the left hand side, after using my initial conditions, I noticed that only two terms included a y of s. I combined those like terms, factored out a y of s. Everything else is on the right side. When I divide by s plus 1 to solve for y of s, here I will have to separate those. I joke about this in college algebra. I say divorce those terms. So I'll have to split these terms up so that I can apply an inverse Laplace transform, because as of right now we know no other tool. Now somebody mentioned another idea. I haven't taught like convolution, I haven't taught those yet, so we're just using the rules that we built in 7.1 right now. And then the 10s, I'll hang on to that. It's up to you if you want to combine these, or I might just hang on to that and come back to it. I will have to use partial fraction decomposition. I do have quadratic terms. They're prime quadratic factors. What I mean by that is if you tried to factor these over the reals, you could not. They have complex roots. And so I split this up into a linear function over s squared plus 2, another linear term over s squared plus 1, and I'll just hang on to the 10s over s squared plus 2. I don't even need to mess with it actually right now. I just need to find a, c, d, and e. If I combined these, getting common denominators, I would have as plus c times s squared plus 1, so you'd have like the cross multiplication idea here. ds plus e times s squared plus 2, and that would all equal 2. That gives me a system of equations, so I combine like terms, and I have two equations in terms of c and e. Isolating e allows me to solve for c, so I have that e is 2, c is negative 2. A plus d must equal 0 because there is no s cubed term. A plus 2d must equal 0 because there is no s term, linear term on the right side. Because of that, I'm able to solve that d and a must be equal to 0. So these will actually not be a problem whatsoever. That tells me that I only have a constant over s squared plus 2 and a constant over s squared plus 1. And you perhaps could have done that a little bit faster. Once you get really fast with these, then you may not even always need to go through this process, because sometimes you can pick up those common trends faster. But this I went ahead and detailed so that you could see how I split those apart, and I still have this 10s over s squared plus 1. I kept that over to the right because right now I just have these fundamental rules, and s over s squared plus 1, the inverse of that, the inverse Laplace transform, is cosine of t. So the 10 remains as a constant. 1 over s squared plus 1 is the inverse Laplace transform would be sine of t, so the 2 remains. This is s squared plus 2 in the denominator. That only looks like the sine term. We only have fundamental rules right now. So if you are using tables or online resources, that is fine. I realize we're all working from different areas, but if it looks more complicated than anything we've discussed so far, then you don't necessarily have to use that yet. And so based on this rule that I have in the right hand corner, if you were to take the inverse, then beta would need to be the square root of 2. I don't have a square root of 2, so I imagine that 2 is the square root of 2 times the square root of 2. That's why I have a square root of 2 that remains, and the other square root of 2 is morphed into the inverse Laplace transform. So the other square root of 2 was used for the inverse Laplace transform to get sine of square root of 2t. So this is number 37. Number 41. Now number 41, this one is more complicated, but keep in mind you're also only dealing with a first order differential equation here. So for y prime, I've used our formulas. For y, I've plugged that in, and for the right side, I used the formula. I used the inverse of the inverse that was given to me. So in the instructions for this problem, they give you the inverse of a statement, and it's equal to e to the negative 3t cosine of 2t. Because that's a one-to-one function, then it automatically tells you could go the other direction, and you can use the table in the back of the book. Don't try to use more complicated formulas right now. They may run you into a corner, and so just use what you were given for this problem, and you should have a line that starts something like this. Now I do realize you have something kind of complicated. In my last video, I hinted that we might have to use partial fraction, or we might have to complete the square sometimes and use partial fraction decomposition. If they had not given you some of this, you'll notice that this would be a case where eventually we will have to complete the square, and I realize that's not everybody's favorite thing. But right now you don't have to, because you'll just apply the formula given. So for the second step, this should be pretty explanatory. From the first step, you'll use the initial value that cancels the y of 0, and so solving for y of s, you'll end up with something like this. So let me talk through where I got this from. So s plus 1 factored out times y of s, so that's my Laplace transform of y, is equal to this expression on the right, which comes from just applying the formula given. Now I notice that denominator is prime. meaning that it doesn't factor over the reals easily. So 13 is prime. That's not the reason, but if you take the discriminant of this quadratic, then you will not get a perfect square. And so this is a prime quadratic. And so when you divide by s plus 1, I'll have an s plus 1, a linear factor in the denominator. Well, on this next step, I went ahead and separated those. I know that I'm going to need to, and I'll need to eventually. So what I did is I imagined, okay, I'll have s plus 3 over the product of s plus 1 times this quadratic. Well, go ahead and split that up, and I know that I'll have possibly a linear factor here, so as plus b over that prime quadratic, plus a constant over that linear factor. Now, a linear factor in the denominator is the simple case. You can use the substitution method or the cover-up method. And so, because c will be the constant over the expression when s is equal to -1, so you'll substitute s equals -1 into this. By substituting in the top, you'll have 2, and by substituting in the bottom, you'll have 8. C must be 1/4. That immediately tells me this factor right here, so C must be equal to 1/4. So this term, I have every constant for it. On the left-hand side, we still should continue that. I know that as plus b times that denominator, s plus 1, the new denominator, plus 1/4 times the s squared, and the 1/4 comes from the c, times that denominator, and you don't have to expand it since you will need to do the algebra though. I went ahead and did that. If you don't expand it, you can use substitution. So if you prefer the method where you substitute values for s, then -3 would be easy to substitute. So if you don't want to multiply this out because you want to substitute values, then that will also work just fine. Multiplying that out, what I did here is I combined like terms, and that gave me a system of equations. So the constants, b plus 13/4 must equal 3, therefore b was -1/4. Then I moved to the coefficients of s squared. Because the right side has no s squared, then I know a must be -1/4. That allowed me to solve, or check my work, basically, because I've really already solved for a and b, and if you plug in the values I have, then that indeed works for the linear terms on the left and right. So I got that a is equal to -1/4 and b is equal to -1/4. When I substitute those in, I factored out a -1/4, I have an s plus 1 on top. This part of the problem will be an easy thing to apply the inverse Laplace transform, but this is a little more tricky. Now what I was given, I have to have an s plus 3 over s plus 3 squared plus 4 in order to use the formulas given, and I don't have that. I have an s plus 1. Well, you can always add and subtract at the same time and not change something. So because I need an s plus 3, what I've done is I've added 2, and I've subtracted a term with 2 of those as well. So if you'll notice, from the second to the third line here, I've added and subtracted at the same time. So I haven't changed it, but now I can use the formulas. So from the term here, using the formulas given, this will directly give you cosine of 2. 2 comes from the square root of 4, 2t. And then for the, you'll notice this is a negative and a negative, so I have a plus 1/4. And this is the formula for e to the -3t sine of 2t. And this last term, that's a piece of cake, 1/4 e to the -t. And so you've now completed this problem. Now, for these problems, you already had methods before that would have solved this. This was a simple homogeneous equation with constant coefficients. This would have been a piece of cake to use undetermined coefficients. It is an easy problem if you use undetermined coefficients, a little bit longer for Laplace transform. However, these problems are helping us understand Laplace transforms when we need to apply them for very complicated formulas. So keep that in mind. In the future, you wouldn't want to use Laplace transform to solve this, but because we're trying to build this understanding, we have to start with some easy ones so that we understand how to use this when they do get complicated and we couldn't use method of undetermined coefficients. Now remember, variation of parameters would have worked as well. but actually it wouldn't have been necessary since this is homogeneous. Now for the second one, variation of parameters would have worked. Method of undetermined coefficients would have worked. You can decide which one is your favorite. One of the nice things about Laplace transform is when you have these initial values, they do cancel suddenly. If you had used method of undetermined coefficients or variation of parameters, you still would have needed to solve for those constants. So that is something to keep in mind. So method of undetermined coefficients would have worked on this problem. This is a first order differential equation. The problem with method of undetermined coefficients is product rule, and that could have taken you some time. So you can kind of get a feel for your preferred methods. Chapter 7 is about learning about this new method, and as we go on, we'll learn a couple new properties that you can also apply. So keep that in mind.